Jonathan Woodbridge. Jonathan's here from Endgame, so data science to Endgame. Joined there in 2015 after spending several years at Sandia National Labs. In Livermore here or over in New Mexico?
New Mexico.
All right, okay. So please join me in welcoming Jonathan.
Well, you're welcome for keeping you here while you're very hungry. So Endgame is a cybersecurity company. We exist in something called the EDR market, which is endpoint detection and response. All this really means is that we run in these big networks. We develop a small piece of software, sensor software, that runs on endpoints. Endpoints would be laptops, desktops, servers. And they kind of run in a stealth mode, so you can't see us running. And even more importantly, the adversary can't see us running. And we run a bunch of protections to keep adversaries out of your network and off your boxes. So to understand our product, you kind of have to understand the attacker lifecycle, which are these arrows up here on the board. But basically, this describes the cycle of an attack. So first, an attacker will figure out, hey, I want to hit Sony, for example. Here are the people that I want to hit. I think we can get into the network with these people. They do some sort of exploit. It could be a phishing. It could be some sort of drive-by where they go to a website and accidentally download malware. And then from there, they try to get some sort of persistence in your network. They try to move from machine to machine. And then they may want to exfiltrate data or do any sort of other nefarious acts to the network. So Endgame offers something called a layered defense. And basically, this means that we have lots of different defenses. The idea is that one defense is not going to be 100%. So you have as many defenses as possible so that you are more likely to catch the adversary. So on the bottom, there's a bunch of our defenses. We have a lot more, actually. This slide's a little old. But I'm going to talk about Endgame's MalwareScore. So before I get into that, a lot of our competitors are trying to say that malware doesn't matter anymore. They say, oh, there's all these new attacks. You don't have to worry about malware as much. That's why our company focuses on these other attacks. And I would agree that you do need to focus on a lot of attacks. They call this the attack surface. Basically, there's a lot of ways to get into a network these days, especially with IoT. But these are a few countries and companies that would probably disagree that malware is not important. Some of them are a little scary, actually. So in the top middle, that's the Ukrainian flag. So the Russian government deployed malware to their Android phones, to the military, and were able to track their military through their Android phones. That's kind of scary. Some of them are a little bit, I guess, a little more funny. So on the bottom, that's the Mooney symbol for those who live here in the San Francisco area. If you live in San Francisco, maybe 6 or 8 months ago, you might have remembered there was this day where we got free rides for the whole day. And that was because they got ransomware. So it was all free for the day. But yeah. So anyway, so a couple years ago, maybe it was 3 years ago, this is a colleague of mine. He's Phil. He's very smart. He saw this Kaggle competition on Microsoft. And he kind of looked at it and said, oh, this is kind of a cool idea. And basically, the idea of this Kaggle competition was they have a bunch of executable files. So executable files are things that you run on your Windows box. So we're all focused on Windows right now. But these would be things like Internet Explorer, Microsoft Word, Excel, PowerPoint. These are all executables. There's also malicious executables. These would be things like password stealers that run on your machine. And they look at your keystrokes, for example, and then steal your passwords. Microsoft gave this huge data set, all labeled. And Phil said, oh, this is so easy. I'm going to knock this out of the park. His boss gave him a couple of months to work on it. And I think he actually got like top 5 in the Kaggle competition, which is pretty good. But the more important thing was this was kind of like a good proof of concept, and we decided that Endgame could get into this market. So before I get into the details, MalwareScore is a machine learning-based malware classifier. So we are only looking at executables here. We're not looking at things like PDFs. We're not looking at Word documents. But we're just looking at executables like Microsoft Word, malware, things like this. So this is kind of your standard supervised machine learning, where we take in a bunch of samples. These samples are labeled. We actually train our classifiers on about 60 million samples right now, so it's a lot. So the samples come in, we extract features from those, and then we feed those to a machine learning algorithm. So these are things like SVMs, random forests, gradient boosted decision trees. And out comes this model. And this model is kind of magical, where you can give it a new sample, maybe an executable that you don't know. Maybe somebody sent you some executable in your mail, and you don't really want to run it because you're smart. And you pass it to our model, and our model will give you a score. And of course, a score doesn't mean anything to us. So we have to make some translation of this score into an actionable item. So we typically choose a threshold. I'll say we choose one threshold. We actually choose a few because we have different actions depending on what this value is. But for the sake of this presentation, let's assume we have one threshold. And let's say it's 0.73. This is totally made up. But if it's greater than 0.73, we say it's malware. If it's less than 0.73, we say it's benign. So this is kind of standard machine learning stuff. But there's a lot of tasks that are kind of not obvious. So I did a lot of machine learning and stuff in grad school, and we pretty much followed that basic model. You make an ROC curve, and you say, oh, it's fantastic. I'm going to publish a paper. But unfortunately, that doesn't actually work in the real world. So there's a lot of these tasks that we have to focus on to make something that's actually good enough to run on our customers' networks. So that's the first point here that I'm going to talk about, is how do we know when our model is ready to actually run in a product? Number two, there's problems with data. Data tends to be biased. And what that means is the data does not represent what data really looks like in the real world. So if you take all the data out of the Microsoft Kaggle competition, it definitely does not look like the real world. There's also a problem in security with an evolving adversary. Adversaries are always evolving. They're always getting better. And we have to keep our classifiers up to date. And finally, I'm just going to talk a little bit about why we choose to use gradient boosted decision trees as opposed to some other popular malware algorithms. Or, I'm sorry, machine learning algorithms. So first, this is very basic machine learning stuff. A lot of you have probably learned this before. This is called a ROC Curve, receiver operating characteristic. And basically, this just kind of describes how well your classifier operates. So on the left-hand side, we have true positive rate. All this means is, given all the malware that you classify with this classifier, how much of it do you classify as being malware? How much do you get right? So you want true positive rate to be really good. False positive rate says, of all the benign stuff that I see, like Internet Explorer or Microsoft Word, how much do I classify as being malware? So this is bad. So you want this to be as small as possible. Here is, this dotted line is chance. So let's say our classifier was a coin and we flipped it. If it was heads, we said it was malware. If it was tails, we said it was benign. It'd be a terrible classifier, and you would basically be on this dotted line. So obviously, you want your ROC curve to be much higher than that dotted line. And so just to kind of understand how these ROC curves are derived, we basically look at the threshold that I talked about before. And for every value of that threshold, we calculate the false positive rate and the true positive rate. So let's assume we set, apparently I have a meeting. So let's say we set the threshold to 0.95. That's a really high threshold. That basically means that we're going to classify nothing as malware almost. And so obviously your true positive rate is going to be really low, but your false positive rate is going to be really low. And if we go to the other end of the spectrum, let's say our threshold is 0.1, then we're going to basically classify everything as malware, because almost everything is going to have a score higher than 0.1. Very little is going to be below 0.1. So our false positive rate is going to be really high, but our true positive rate is going to be really high. And so the idea here is you want to find some balance where your true positive rate has a good balance with its false positive rate. So just to kind of drive the point home, it's good to have a true positive rate. It's very bad to have a false positive rate. And if you want to sum up a ROC curve with one number, they have something called an area under the curve. This is exactly what the name says, and it's just this pink area here. So you want something as close to 1 as possible. All right, so here's some truths to the matter. False positives in security are really, really expensive. And let's just make an example. I'll call him Timmy. He's, let's say, in middle school, and he's doing some report for his history class. And I think maybe he's an aspiring data scientist, so he wants to make all these charts, and he wants to use Excel. So he opens up Excel, and then his favorite antivirus software says, oh, Excel is malware. How annoying. So he clicks on the box. He gets rid of it. He says, OK, I'm going to make my charts now. I'm going to go put them in my Word document, and all of a sudden, Word is now also malicious according to his antivirus. Of course, this is wrong, so he has to click through some screens, make it not malicious anymore. Then he goes and uses Firefox. This is really annoying. He uses lots of bad words, and he turns off his antivirus software. So this it's an exaggeration, of course, but this actually happens. So I don't know if any of you have ever turned off your antivirus because you get so annoyed with all the pop-ups that you get. And the problem is that you turn it off, then you're completely open to any sort of attackers. Oops, I'm sorry. And so there's a reality check here. Creating a classifier for malware with a good true positive rate is actually really easy. And a lot of our competitors won't admit to that. And a lot of their marketing material will not really show that. they'll come out and say, oh, malware X, malware Y, we caught it, and none of our competitors caught that. And so the reality here is that anybody with any sort of antivirus can cherry pick malware and say, I catch it and our competitors don't. The real measure is how low is your false positive rate. Because if your false positive rate is high, then no one's going to use your software. And there's a question of how low should your FPR rate actually be, your false positive rate be. And so I have a little example up here. So we run on fairly large networks. So let's assume we're running on 50,000 nodes in a network. So these are 50,000 desktops, laptops, and servers. And let's say, we'll take a very low number here actually, and say that our classifier will classify 100 files per machine in this network. And this is actually low. This is very conservative. This would be 5 million classifications a day. And let's say our false positive rate was 1 in 10,000. Most of you would probably think that's really low, right? That's 500 false positives a day. That's 500 false positives that some security professional has to look at. It may only take a few minutes. They may look up, they may take a hash of the file and realize that they've seen it before. Or it might be a new file, so they might actually have to reverse engineer the file to make sure it's okay. And so most organizations don't have the bandwidth to look at 500 different binaries or executables every day. So there's this saying in machine learning where it's garbage in, garbage out. I'm sure a lot of you have heard this. And the idea is that if you give a classifier bad data, it's going to give you a bad classifier. And so there's a question of where do we get data when we're doing a malware classifier. And there's a lot of sources. Some of them are free, like Kaggle. They tend to not be so good. Some of them are paid sources. One example is VirusTotal. This is run by Google. They have this huge database with a bunch of malicious as well as benign files. There's also customer data. This is probably the best data in security. Bigger companies like FireEye and Symantec, they kind of have an advantage over smaller companies like us because they have more customers, obviously. There's things called honeypots, which are basically these servers that kind of exist randomly in the internet, and they somehow make them really attractive, so hackers try to get into it, and they drop malware and other malicious stuff. And then there's other things like you can check your spam folder, you can scrape things off of like Apache, and then you can also take files out of your OS distributions. But the problem, all of this data is biased, meaning none of this data looks like the real world. So we're going to take kind of a view from VirusTotal. So remember, they have this huge database. There's lots of malicious files, lots of benign files. And on the left-hand side, this is what VirusTotal's world of binaries look like. So they get about 40% malicious files and about 60% benign files. The problem is the real world looks a lot more like this. Almost everything is benign, actually. So in a network, if you have 1 in 10,000 files being malicious, you probably have a lot of malicious files. There's another problem. The benign files in VirusTotal are actually not that benign. They're not malware, but they're not goodware, really. There's a lot of stuff that's kind of questionable, like hacker tools. Hacker tools are not malware, but they can be used to do very malicious things. There's also stuff like toolbars and ads and all this junk that you just don't want on your machine, and probably annoys you every now and then when you download it to your machine. And so we're going to kind of take a look at this data. So let's imagine we took all that data in VirusTotal and we projected it to a two-dimensional plane. And so blue is going to be benign, red is going to be malicious. So on the left-hand side, you can see that we have a pretty good coverage of malware. So VirusTotal looks a lot like the real world in terms of malware. But the blue, the goodware, it doesn't really look like the real world, because the right-hand side would be like your real world, which is kind of well distributed. But here we have not that many samples, and they're all kind of clustered into this one little part. And obviously on the right-hand side, this is your real world, so there's a lot more benign files. And this is kind of what you would expect to see. Now, if we trained a classifier on this left-hand set of data, you would get kind of this weird curve. And you can see that, so basically how this works is the background determines what the class will be. So anything that's in the red areas of the background is going to be malicious. Everything in the blue areas is going to be benign. So you can see that because there's so few examples and they're kind of clustered together, a classifier trained on this view of the world will think that everything is malicious. And by the way, this is all made up data. This is not actual real data. But on the right-hand side, we train the same classifier, but on a bigger set of data that's more representative. You can see that the boundary is much better. And actually, the AUC is a little bit higher. Now, some of you may say, OK, well, there wasn't enough data there, so let's sample more. But the problem is that your sampling is still biased. And what's going to happen is you're going to sample all from that same point. And you are going to reduce something called variance in the model. And what that means is the model's going to be really sure that it's always right. even though that it's pretty much always wrong. And you can kind of see the effect of variance on the right-hand side. You can see those little shaded bars. They're a lot smaller, and that just kind of shows that the model is more certain. And what this is called overtraining, which I'm sure a lot of you have heard of. So there's a lot of other ways to try to fix this sort of bias done in academia, but a lot of it really doesn't work that well. And the reality is, to fix bias, it's really tedious. And we kind of go through this cycle. So basically you start, you get all these, all your data that you want to train on. You get as much data as you possibly can. You try to remove bias as best you can. You create the best classifier you can. You create the best features you can. You really just do the best with what you got. And then you throw your model into the real world. And then it sucks. And you basically learn something from that. So that maybe you have A/B testing, whatever, but you learn something from it. And once you learn, you get new data, new features, and you do this whole cycle again. You do it over and over and over again. It becomes very tedious. It's not very fun at times, but the reality is this is what you have to do to get a good classifier. And so I'm going to go through a few things that we learned. One is installers look very malicious. So installer is like, oh, I want to install Firefox. I download this installer. It downloads a bunch of software, installs it onto my machine, then I can run Firefox. The thing is that there's a lot of malware whose sole purpose in life is to download other pieces of malware. So they look the same. So we figured this out the hard way. Our customers yelled at us. And so we had to go out, find a lot more installers, benign installers, and train on those as well. Another thing that we learned about was there's a lot of benign packed files. So a packed file is basically a binary that's been compressed. And that makes it smaller, but more importantly, it obfuscates the code. So obviously malware writers don't want people to reverse engineer their code and know that it's malicious. But actually a lot of goodware does the same thing because they don't want their competitors to reverse engineer their code. And so we had some troubles with that, so we had to get more benign packed files. And a funny thing is that antivirus actually looks the most malicious out of any goodware because they do all this nasty stuff. So another use case there. Now, there's also this problem where we kind of have this cat and mouse game where the adversary is always kind of one step ahead of security, and they're always coming out with new malware and new techniques to get into a network. So this is kind of the trend of ransomware. I think we had a blog post, one of my colleagues had a blog post last week talking about ransomware, and they had this image showing how ransomware changed from 2013 to 2017. And first of all, like I said earlier, some competitors are saying malware is not that important. You can see that ransomware is only becoming more prominent now. But you can also see that things are changing and things are changing faster. And so this kind of comes into question something called how well does your model generalize? So if I train on all the data up till today, all the malware, all the benign up to today, then tomorrow some adversary comes up with some new ransomware, will my model be correct? So there is kind of a way that classical machine learning handles this. So let's assume this black box is all our data. And what they'll do is they'll say, OK, I'm going to randomly select some data. There are going to be these red boxes here. And this is going to be my test set. So I'm going to remove it out of this black box, and I'm going to train on everything that's left. And then I'm going to test on these red boxes. And if I do really well, that means my model generalizes well. But the problem is this obviously doesn't account for time. If things are changing over time, this is a terrible way to see how well your model generalizes. So another technique that we do is that we actually divide it by time so that we'll train up, let's say we'll train on all the data we have up until March. Then we'll take all the data in April and see how well our model generalizes into the future. And this is one way of doing it. We have a few other ways of doing it, but this is one very powerful way of doing it. So finally, we kind of talked a little bit about data. There's a question of why do we choose the models that we choose? And this really depends on your use case. So everybody's a little bit different. So if you're Google and you're using these huge compute nodes, you can do deep learning and all this crazy stuff because you have plenty of memory, plenty of processing. In our case, we're running these nodes on an endpoint, and it has to be stealthy. So nobody can know that we're running there because we don't want the adversary to get in there and shut down our software. So we need a low memory footprint and a low processing footprint. And like I talked about earlier, we also need to be really low on false positive rates. So we actually wrote a blog post on this if you're curious about how we selected our model. But here are just a few images from that blog post. So we basically did this huge comparison. We looked at tons of different machine learning models, tons of different techniques for extracting features. And this kind of summarizes some of the models that we looked at. First thing I wanted to point out was deep learning. So if any of you are big deep learning people, you might be saying, hey, what's going on here? Why is deep learning doing so poorly? And this because this is actually a little bit biased. So because we're running on an endpoint, we need to keep the model as small as possible. And if anybody does deep learning, I actually do a lot of it. You'll know that deep learning, these are neural nets. They have to be very deep. They have to be very large. And they take a lot of compute power. And unfortunately, we can't run that on the endpoint. So these are actually very small models. And that's why they don't perform very well. And then on the top, gradient boosted decision trees, this is what we actually use. And this pretty much gave us the best trade-off in size and performance. And we plotted this in different ways. So on the left-hand side, this is basically showing the size of our model versus AUC, so smaller model that performs well. And on the right-hand side, it's showing basically how many processes or how many samples can you classify per second. So this kind of gives you a feel of the processing footprint. And so it does pretty well. I mean, gradient boosted decision trees kind of gives the best of all worlds. And so I left out a lot of stuff. So I only have 30 minutes. I could talk for hours on this stuff, and you guys are really hungry. So there's a few things that I left out. One is the data engineering. I'm not a data engineer, so I didn't really want to get into specifics here. But we have a fantastic data engineering team at Endgame, and they've built this huge framework that basically brings in hundreds of thousands of files a day from several different sources, does feature extraction, storage, and when it's time for us to train models, we can basically just magically hit some database and get all our features back. So they make it really easy for us. Another thing is there is a question about how do you actually implement a model in your customer's network. So a lot of people probably use open source, and depending on your environment, you may be able to use open source in the real world. And we do for training. But when it comes down to actual evaluating our model, the open source is just too big. It's too bloated because we have to be so constrained. So we actually re-implemented gradient boosted decision trees for our network sensors. And the nice thing here is that we know exactly what our classifier is doing. We know what the parameters are. We know what the assumptions are. So we can remove all the generalization that they add to this code and make the code very, very small. And so this took actually several months of development, and this is kind of just standard software engineering. Actually, Phil did a lot of this work, the gentleman you saw earlier in my slides. But this requires a lot of unit tests, code reviews, QA, kind of your standard software engineering. So I'm almost done. One thing that I would encourage you to do, so this is VirusTotal. This is actually a website owned by Google, virustotal.com to get there. And it's really cool. If you have any sort of file, it could be a PDF, could be a binary, and you're curious as to whether it's malicious or not, you can actually upload it to VirusTotal. And then it'll run it on 70 or 80 different antivirus software to see if it's malicious or not. We're actually one of them on there. We were added in, I believe, February. And so you can actually test this out for free and see how well we compare with our competitors. We encourage it. And finally, any questions?
Thanks, Jonathan. That's great. So, questions? Yes, sir. Got one right at the side here.
Great talk, thank you. I'm curious kind of what the endgame is for Endgame in an era where there are more and more secured devices where you only run secure code like on iPhones and Androids and iPads and so on. It's not exactly a growing market where you've got lots of more servers and laptops. What's the thought?
Well, I think I might disagree with you that it's not a growing field.
Okay.
The number of breaches increases every year by a lot. I think somebody is going to be speaking from Lookout later, so he'll probably talk a little bit more about Android. I'm not as familiar with the mobile market. We're more worried about Windows, Linux, OS X. But like I said earlier, the attack surface, the ways of getting into a network just keep growing. And the size of the cybersecurity industry is only growing. And it's going to be growing for a long, long time. You can look at things, just last weekend, there was an election in France, right? And there was a lot of hacking there. Our elections, of course, was under some scrutiny as well. So I don't actually think that the market's going to get smaller by any means. I think it's going to be growing almost exponentially, probably over the next 10 to 20 years.
Thank you.
Yes, right at the back.
got a question about your implementation. Are you constantly running the model every time you see an executable being downloaded, or once you find and positively identify something that is malware or malicious, are you logging that and saying every time that we see this again, it's we're going to flag it as something that you shouldn't open?
Yeah, so I think there's a few questions in there. So we can't retrain our models on a single file because we're training on such a huge scale. So we do train kind of new models every couple of weeks or so, depending on how, like if we see our classifier starting to degrade in performance, we'll definitely kick off something a little bit earlier. But you also bring up another question of, what if you know a certain file is malicious or not? Or maybe it's a false positive, right? And so in that case, you can do some sort of signatures. You can do something as simple as taking a hash, which is a 64-bit hash, and you can say, if I see this hash again, I know it's benign, so just ignore it. And then there's other more complicated signatures. There's a tool called Yara, which basically is a regular expression over binary files. And so you can write rules like that. But in terms of retraining, we are constantly retraining. But it also gets into the generalization. So we don't want to constantly retrain every day because it's very computationally expensive. So we want to make sure that our model generalizes to new stuff.
Is there something different you do for zero-day attacks?
For zero-day attacks, well, again, that gets back to generalization. So we hope that our model, so we craft our features such that they're a little bit more generalized, and so that we hope that we do catch some 0 days. Again, MalwareScore is only one small part of our layered defenses. And so there's something up there, CFI, which is one of our techniques that is very good actually at finding 0-day exploits. And then we have a bunch of other detections that will catch 0 days as well. But 0 days are hard, right? Because we haven't seen them before. So we do the best we can. And if we do see certain protections starting to degrade, we'll retrain and get them back up to snuff.
Awesome. Thanks so much.
All right.